Welcome back. In the last class, we extensively discussed carbon 13 NMR, and I discussed how we are seeing the carbon 13 spectrum, especially when it is directly attached to protons, the type of splitting we are going to see for a CH3 carbon, CH2 carbon, CH carbon, and also we saw what happened to the long range couplings of carbon to protons, how it is going to be affected, and we also saw that chemical structure of carbons are similar to the way the chemical structure of the protons are influencing proton chemical shifts. The way the proton chemical shifts are influenced by various factors, similarly the carbon same factors affects the carbon 13 chemical shifts in the same manner. Most important thing I pointed out, because of the natural abundance of the carbon 13, it is not possible or practically is impossible to see all the carbons in a molecule in carbon 13 state. As a consequence, we have different carbons in different carbon 13 state corresponding to n chemically equivalent carbons in a molecule. There is going to be n different chemical isotopomers. As a consequence, what you are going to see is the superposition of the spectrum of each isotopomer. That's what I said. Carbon 13 spectrum is the superposition of the spectrum corresponding to each isotopomer. On the other hand, in the proton, I said it is a spectrum of a single molecule. But the carbon 13 spectrum is not from a single molecule. It is superposition of the spectra of n different isotopomers. Okay. And finally, we came to the situation we saw. This is the type of spectrum generally we observe for a given molecule like this. But if I give you the spectrum like this, the interpretation is as difficult as that of the carbon. I'm sorry, as difficult as that of the proton spectrum. You understand? It is a very complex carbon spectrum, similar to that of a proton spectrum. Now, how do you simplify? See, first of all, the carbon 13 spectrum is always recorded with a decoupling mode. This is a proton coupled to carbon 13 spectrum. As I saw, this is a CH3. This carbon will be a quartet, this will be a quartet, this will be a triplet, this will be triplet, this will be doublet, like that. So varieties of multiplicity pattern you are seeing. In fact, if you take a fully coupled carbon 13 spectrum, there will be long range proton carbon couplings also. We cannot deny that. So everything is possible. As a consequence, carbon spectrum is highly complex. The question is, how do you see? The one way of simplifying the carbon spectrum is, generally, carbon spectra are recorded with broadband proton decoupled. You see, we always get a broadband proton decoupled carbon 13 spectrum. What do you mean by broadband? That means the entire range of carbon chemical shifts, we remove all protons that are coupled to carbon. This is called decoupling. See, completely broadband, entire range, we remove proton carbon couplings. As a consequence, what happens? No carbon is coupled to any protons. Understand? No carbon is coupled to any of the protons. Then what will happen? Each carbon is going to give you a single peak. When you take the broadband decoupled spectrum of carbon, broadband decoupling means I am decoupling only protons. Remember, carbon attached to all the protons I am removing. If it is attached to different heteronuclei, that's a different question. I am not removing that. That coupling will be there. That's what I said. The beauty of NMR, only particular nuclei we can decouple. So since in these molecules, most of these molecules, organic molecules, protons will be invariably present attached to carbon, which is giving complexity for the spectrum. What we do is, we do at a time, remove all the couplings of protons with carbon. That is the best way. In which case, you get one carbon for one peak for one carbon. What does it mean? If your molecule has 10 carbons, you get 10 peaks. If your molecule has 6 carbons, you get 6 peaks. That's all. Very simple. So what we do in the case of the broadband decoupling carbon 13 is like this. See, on the carbon 13, that's what we are detecting. I am going to apply radio frequency pulse and then start collecting the free induction decay. Apply radio frequency pulse on carbon, start collecting the free induction decay. And simultaneously, right from the beginning of the RF pulse, when I apply, all this can be timed very properly. Don't worry. When I come to experimental setup, I'll discuss all those things. Exactly at the point when you apply RF pulse, I can switch on decoupler. So you have the proton channel. There are different channels, modules in the NMR spectrometer. I am going to apply carbon 13. In the carbon 13 channel, 90 degree pulse for detection. In the proton channel, I am simultaneously applying a relatively high power so that I will decouple all the protons with carbon. How we do? This is what we do. At the proton frequency, at the center of the proton frequency, what is center of proton frequency? We know the proton chemical shifts 0 to 10 ppm or 15 ppm. Go to the center of that. Let us say I take 0 to 10 ppm. At 5 ppm, I am going to have an offset. That is called decoupler offset. I sit at the center of the proton spectrum and apply a radio frequency pulse. Remember, this is another radio frequency pulse, not this one. This is for detection. At the proton channel, you apply another radio frequency pulse simultaneously with little high power and continuously. It is a continuous power we apply right from the beginning of the pulse till the end of collection of the signal of that is FID. We keep applying the radio frequency pulse, and then we start applying the radio frequency here and start collecting the signal. This is always on. See here in the figure in the pulse sequence we can see power on the carbon the proton channel is always on right from the beginning till the end of collection of data FID. Whereas carbon 13 we start collecting the signal, simply apply 90 pulse, start collecting the signal like you do routine 1D collection of the data. There is no problem at all. Okay. The question what happens in the decoupling, everything I'll explain to you when we come to decoupling. When we discuss more about decoupling, when there is an opportunity, we will do that. And now let us see what happens if I do the decoupling of carbon 13 spectrum. Take this molecule. It is called some phenol or something. At 75 megahertz, when I take the carbon 13 spectrum, this is what it is. Very clear. You all know that. This is a CA3, this one, which comes at high field, and this carbon is a quartet. You know why? Because attached to 3 protons, chemically equivalent. This CH2 is a triplet because it is attached to 2 protons. So it is a triplet. And each of these aromatic carbon is a CH carbon. So it is attached to, directly attached. A proton is there. It is coupled to that directly attached proton. Each carbon is going to be a doublet. And this quaternary carbon, carbon 6, is not coupled to anything. So it is a carbon which is not coupled to any of the protons. This gives a singlet. This is what it is. It is a spectrum, normal spectrum. If you say take in the carbon 13 spectrum without doing any decoupling, it is only this part of the spectrum is that. But bottom what I showed. This is not applied at all. Now, if I do the real decoupled spectrum, so like this, while collecting the signal, I also apply second radio frequency pulse at the proton frequency to saturate the protons. That means to decouple all the protons coupled to carbon, and this is what we are going to get. Look at this, what happened? The spectrum got significantly simplified. Look at this, these 4 peaks which were there is a quartet, they all collapsed into a singlet because now it is not coupled to CH3 protons anymore. There is no splitting of the energy levels or no splitting of the peaks. They overlap, they collapse into a singlet. See? Now, similarly, this triplet collapses into a singlet. All these doublets of the aromatic protons collapses into a singlet. Very, very interesting thing also happened. What is the interesting thing why it happened? Look at this one. All the signals, intensity is much more. Because there is no more additional splitting. All of them collapse. Intensity will add up. As a consequence, the signal to noise ratio becomes better. So the advantage of taking the decoupled carbon 13 NMR spectrum is the signal to noise ratio goes up, one thing, and the spectrum gets simplified. No more complexity. So you can directly count the number of peaks and start telling how many carbons are there in this molecule. Simply look at this one. There is a proton, there is one carbon, two carbon, three, four, five, six. There are six peaks. You count the number of carbon. This is one carbon, two carbon. These two are identical because of symmetry. These three. These two are identical, four and five. And this carbon, six carbons are there. You may understand. You ask me the question: what are these three lines coming? This is the thing because of CDCl3 we have used. It is not 100% deuterated. I'm sorry. This is the CDCl3. The carbon is coupled to deuterium. Okay, you see in the proton it is not 100% deuterated. We get a peak with residual proton, but here we are directly seeing the CDCl3 peak. Carbon which is directly attached to proton as deuterium. Carbon which is directly attached to deuterium. As a consequence, deuterium has spin 1. Remember, deuterium has spin 1. As a consequence, then each line of this carbon peak is split into 3 lines of equal intensity. You understand? This is a CDCl3 peak coming because of carbon directly bonded to deuterium, which has spin 1, and this carbon split into 3 lines of equal intensity due to deuterium. So this is why you get this is a solvent peak. Don't worry, we'll come to that later. Now we went back. Let us go back to the cholesterol molecule. Earlier we saw that, and this was the complexity of the spectrum which I showed. Okay, so this was the earlier one we saw. Now we go back and see that spectrum and compare with the present spectrum, which is obtained with broadband decoupling. Continuous wave CW broadband decoupling. Look, this quadrant is collapsed into a singlet. This doublet collapsed into a singlet. You see? Now, such one or two I have highlighted just to get you clarity. See, this 4-line pattern 1331 became a single line, and this two doublets were there. That it became only 2 singlets here, and this is again a doublet became a singlet. Look at the signal to noise ratio. Look at the noise of the spectrum here. This is a noise. This noise is much more compared to here. So signal to noise ratio is considerably improved in the broadband decoupled spectrum. You get the spectrum faster because you don't need to acquire more number of signals because the signal to noise ratio is quite high compared to this. This is the biggest advantage. Not only it simplifies the spectrum, signal to noise ratio is also better. As a consequence, you can get the spectrum faster. It doesn't take much time to get the good spectrum. That's the one important point. So as an example, you can see how the complex multiplicity pattern sometimes you see in this case. In the previous example, you knew these are all identifiable doublet quartets. Consider a situation like this. Here, the triplet is overlapped. It is not only identifiable triplet. One of the peaks of the triplet comes here, one of the peak comes here, and this triplet peak comes here. They are all crossed over. There is an overlap. Peaks are not clearly identifiable. They are completely crossed over to different regions. If that is the case, how do you identify that? This is the spectrum of sucrose in water. In which case, this spectrum complexity is difficult for us to identify which are the triplets, which are the quartets, which are the doublets. But decoupled spectrum, easily we could identify in the sucrose, there are 12 carbons, or we are observing only 12 peaks. Now the question I will ask you, what is happening to D2O peak? Why I am not seeing? I saw the solvent peak CDCl3. Remember in the previous example, carbon was directly coupled to deuterium. Deuterium is spin 1, gave carbon 3 lengths of equal intensity. But there is no carbon here. So when you use the D2O as a solvent in carbon 13 NMR, you will not see any solvent peak at all. There is no residual solvent peak. Duty, is it not? Nothing is there. You get directly get only peaks from your sample. and 7 carbons in this molecule gave me 7 signals. I just want to tell you one interesting point. You count the number of carbons. There is no symmetry in the molecule. 1 carbon, 2, 3, 4, 5, 6, 7 carbon. You count 7 peaks are there. 2, 3, 4, 5, 6, 7. But do you observe one difference here? Why all the carbons are not of equal intensity? If one carbon is there, one peak, there are 7 carbons, 7 peaks. Why there is a difference in the intensity of the peaks? How do you understand that? This is another important point you must know. This is because different carbons have different relaxation times. So they relax. I will talk to you more about relaxation when. In fact, we got an idea of in the 1 or 2 classes. First class, I explained to you what happened to the FID. It relaxes back to z-axis with the spin lattice relaxation. It defaces in the xy plane due to spin relaxation. T1 and T2 concept I told you. So how fast these signals from each of these carbon will come back to thermal equilibrium defines the relaxation time T1, and they are not same for all the carbons. They are different for different carbons for various reasons. The relaxation mechanism is different for each carbons. As a consequence, what happens? You will not get peaks of identical intensity. You can get it still. You know what you have to do? You have to do an experiment wherein when you start applying one person collect the signal, if you want to add, keep on adding the signal, collecting for more signal averaging for better signal to noise ratio, before you apply a second pulse, you have to wait for a longer time. How much time? When I come to practical applications, practical difficulties and NMR, recording NMR spectra, in the practical aspects, I will discuss those things. The delay between one pulse you apply and then again second pulse should be at least 5 times the largest T1 of the molecule, peak, largest T1 of any carbon. Let us say this carbon has a relaxation time of 5 seconds. This has a relaxation time of 10 seconds. This has a relaxation time of, let us say, of 20 seconds. Don't worry about 10 or 5. One which is largest relaxation time, the one carbon which takes more time to relax, take that carbon. Increase, find out what is the relaxation of all the carbons. And the one which has the longest relaxation time, this takes 20 seconds. 5 times that 20 seconds you have to take. 5 into 20, 100 seconds you have to take. And if you give the relaxation delay between the pulse, you first apply a pulse, collect the signal, give a delay, again you apply the pulse and collect the signal. You can do this signal co-adding of the signals. But then before you apply another pulse, you have to wait for 100 seconds. If you do that, then all the carbons would have relaxed back to thermal equilibrium. Then you will get equal intensity. But normally we don't do that because it takes a lot of time. I tell you, in the practical aspects, we say what type of pulse we apply and how much time we wait, everything. As a consequence, you don't get peaks of equal intensities. Otherwise, we should expect peaks of equal intensity. You can, if you are very particular about these things, you have to wait for 5 times the longest T1 of the particular spin in this molecule or particular carbon, and then acquire the data. So the types of decoupling what we do, I said what we do in the case of decoupling is this. There are varieties of decoupling we can do. Remember, in the experiment I showed, we applied the radio frequency pulse and started applying the RF pulse right from the pulse to end of acquisition of the data. We can do many things. We can keep the decoupler power on all the time here on the proton channel, even during the relaxation time here, and collect the signal. Or I can switch off the decoupler time here and have the decoupler on only during acquisition of the data. Or I can keep the decoupler on only during the relaxation time and switch it off during acquisition of the data. Or I can do one more thing. I don't switch on decoupling power for a long time and apply only for a short duration. Okay. And another way I can do inverse gated decoupling I can do. So there are variety. This I'll explain more later when I come to that. So there are several ways of doing this decoupler. In this case, decoupler is on for a short pulse, and I'm collecting the signal in the proton, where I'm decoupling the X nuclei. In all other cases, decoupling power is applied on proton. This is an inverse gated decoupling. I'll come to that later. We will explain each of these things now. Okay. So there are several modes of decoupling, doing a broadband decoupling. And X means it need not be carbon. This experiment can be done for any heteronuclei. It can be phosphorus, it can be nitrogen, anything which is coupled to proton you can remove. Mind you, in the present day spectrometer, it is not only carbon. We can detect carbon, decouple proton. You can detect phosphorus, decouple carbon. Varieties of things are possible now. Okay, but this is for chemistry for people. I'm talking about carbon NMR. So basically, we do broadband decoupling of protons. This is a situation. What will happen in this case? There is no decoupler power on the proton channel at all. What does it give? It gives you fully coupled carbon-13 spectrum. There is no decoupling at all. Each carbon will be coupled to the protons attached to it and also remote protons. Protons which are attached to carbons which are 2 bonds away, 3 bonds away. It is coupled to this. So it is called a fully coupled spectrum, no decoupling. It is a complex spectrum generally. And signal to noise ratio is much less. I can consider a situation like this, where the decoupler is on throughout the experiment. In this case, what is happening is I will use the word called NOE, which next class or another 1 or 2 classes I will discuss more about NOE. Both decoupling and nuclear overhauser effect takes place. In this case, it produces decoupled spectrum with enhanced intensity. What NOE does is it will give you enhancement in the signal intensity. That's the point you remember till you understand NOE. When I do an experiment of broadband decoupling with NOE, not only you get a decoupled spectrum, you get enhanced intensity because you can increase the signal to noise ratio in addition to collapsing of the lane because of decoupling. There are two things happening. Here decoupling will collapse the multiplets. I showed signal intensity goes up, signal to noise ratio goes up. In addition to that, another factor called NOE which adds to increased intensity. We'll discuss NOE later. And actually, this is what you can record in the routine carbon-13 NMR. Another is called gated decoupling. What is gated decoupling is I apply power only during the relaxation time and no power at the time of acquiring the data. See, this is X nuclei, carbon. I'm collecting the signal in the carbon channel and no decoupling is done at the time of acquiring signal. Only before the relaxation time, before the pulse, I am applying RF power for proton channel. It means there is a NOE here. Signal enhancement is there during acquisition time, but at the same time, coupling is retained. This is called coupled spectrum with NOE enhancement. You are going to get a spectrum with the enhanced signal to noise ratio because of NOE plus coupled spectrum. This is what we are going to observe. This is called gated decoupling. Also, we can do inverse gated decoupling. That's also possible. What we do is we apply a power and pulse on the proton channel. Do not apply any NOE at all. There is no RF power at all. Do not apply any RF power during the relaxation time and apply RF power only during acquisition. This means no NOE during acquisition and no coupling here. But here we are removing the coupling. So it is a decoupled spectrum without NOE. Understand? This is a spectrum. This is NOE is not going to show up in the spectrum, but at the same time, we are going to get the completely decoupled spectrum, no coupling at all. The question is, this we have to discuss much more. I have not talked to you about NOE everything. Why NOE is not developed even though power is applied here? Of course, there is a way that now once already the acquisition has started and the transverse magnetization is not going to be affected here. See, as a consequence, NOE will not show up in the spectrum. NOE is an extensive discussion I will do later. And now let us compare the spectrum, varieties of spectrum for a molecule like this. The same sucrose molecule in D2O, I took. It is a carbon-13 spectrum. Look at this. All the 4 experiments I am comparing. No decoupling, no NOE. What does it mean? There is no RF power in the proton channel at all. I am simply observing the signal. Proton carbon 30 signal, right? Send a RF pulse, 90-degree pulse, collect the free radiation decay and detect the signal. No decoupling power at all. But here, gated decoupled, that means there is a coupling plus NOE. This is inverse gated decoupled, decoupled, no NOE. This is a broadband decoupled. That means decoupling plus NOE, both are present here. Look at the growth in the signal to noise ratio as you go from one experiment to other experiment. You look at this signal to noise ratio, look at this one. What an enormous gain in the signal to noise ratio. This is the experiment which we normally do. As a consequence of this type of experiment, you will save a lot of experimental time. This carbon, this spectrum if I have to take, carbon spectrum, it will take me 1 day. And this will hardly take me half an hour. See the difference? And this is what normally we have to do. So this gives you an idea of decoupling and what type of decoupling you have to do. Don't worry. Simply remember, you have to do broadband decoupled spectrum with NOE in the routine case. This is what you do. Nowadays, of course, you can do all those things with pulse sequences. I'll tell you later. And of course, if I look at the carbon 13 spectrum, number of peaks again, like in proton, if there is symmetry in the molecule, symmetry simplifies the spectrum. Okay, look at this molecule. Is there a symmetry axis? Of course, there is a symmetry axis along this. I have just tilted the molecule later like this. And how many carbons are there in this molecule? This and this are equivalent. This carbon and this are equivalent. This and this are equivalent. This and this are equivalent. So 1, 2, 3, 4 different types of carbons are present here. 4 peaks you get. That's all. Look at this molecule. How many peaks I am going to get here? We are only 2 types of carbon. These all CH3s are equivalent, and these 2 carbons are equivalent. As a consequence, you get only 2 peaks in this molecule. Now, we will predict the number of carbon peaks you see in these molecules. How many we can get in this molecule? Look at the carbons which are chemically equivalent. This is equivalent to, I assume there is a symmetry along this axis. There is a symmetry. This carbon is equivalent to this is equivalent to this, and this are different. So how many are there? There are 4 different carbons, you should get 4 peaks. Now count for this. 1, this is equal, these 2 are equal, 1 peak, this is different, 2, these 2 are equivalent, 3, this one, 4. Where is the 5th one? This 1, 2, 3, 4, and 5. Okay, you have to count this ipso carbon with quaternary carbon also. What about this one? You simply count 1, 2, 3, 4, 5, 6. This one, all are equivalent here. There is no symmetry. Oh, there is symmetry, I think. 1, 2, 3, 4, and 5. There are 5 carbons. So you can predict carbon 13 spectrum use the carbon 13 spectrum to predict the reaction code that takes place. Look at this molecule. Let us say somebody is doing a reaction. What the reaction? Let us not worry. Now the question is whether we got this product or this product. What is the answer? Let us assume I don't have proton NMR at all. I have to solve this problem only with carbon 13 NMR. How do I do that? Let us take the carbon 13 spectrum of it. If this is my molecule, there is no symmetry here. 1, 2, 3, 4, 5, 6. There are 7 clines. There are 7 chemically inequivalent carbons. I must get 7 lengths here. If this were to be my molecule, if that were to be the product, then there is a perfect symmetry along this. You should get 5 different carbons here. You get 5 lengths. So carbon 13 NMR will identify which is your product, this or this, from just because of symmetry considerations. You look at the symmetry of this molecule and then find out the number of peaks available or what you going to get in the carbon 13 spectrum. Based on that, you say this is the product or this is the product. Now let us start interpreting some of the simple carbon-13 spectra. Acetone, the solvent which we normally use. This is the molecule. How many peaks you expect? CH3 carbon and CO carbon. There are only two carbons. One here, one here. Then what is this? The CdCl3 carbon coupled to deuterium spin 1. It is a 3 lengths of equal intensity. You got this. Okay. What about this one? Methyl acetate. CH3CO, CH3. Now there is one type of carbon is CH3, other is OCH3, and one is CO carbon. So you expect 3 carbons. This is CdCl3. This is C double bond O. What about this one? This is OCH3 and this one CH3. Using the same like what you do for analysis of the proton spectrum, same consideration depending upon the electronegativity and you know which proton comes at high field. Similarly, use the same logic and say which carbon comes at high field and then start making the assignments. So this is ethyl acetate. How many equivalent carbons are there? You can see 1, 2, 3 and 4. 2 CH3s, 1 CH2 and 1 CO. Look at this one. This is a CO. This is OCH2. This one CH3 and this one CH3. Okay. Now go to ethyl propionate. There are 1, 2, 3, 4, 5 carbons. Where are you seeing? You see here 1, 2, 3, 4, 5 carbons are here. 1, 2, 3, 4, 5 carbons are clearly visible. You can find out what are the CH3. CH3 generally come at high field. This is a CO carbon. This is a CH2 carbon. This is CH3 carbon. This is CH3 carbon. This is OCH2 carbon. Of course, I know these two are CH3. This is CH2. This is OCH2. This is CO. Very easily we can continue. Similarly, for a molecule like this, we have 1, 2, 3, 4, 5 carbons. 5 different peaks are easily identified. CH3, CH2, 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 OH. I know it comes downfield. Now, among the 3 protons here, which is which? How to identify that? Which CH2 is this? How did I make this assignment? We will come to that. You can utilize the knowledge of the proton chemical shifts, and then we can do that. Okay, we will come to that later. We knew how to assign proton based on this is a triplet, this is a quadruplet, this is triplet of triplet. All those things we knew. Same way, once you assign the proton spectrum, use the proton chemical shift knowledge, and we can make the assignment of the carbon. We'll do that when you come to the two-dimensional HSPC spectrum. Now, this is a molecule where it's a fluoroacetone. One fluorine is present here, and it is a proton decoupled spectrum. What does it mean? I decouple all the protons to carbon. Of course, in the previous molecules also, these are all proton decoupled. Here I'm specially mentioning because remember, I'm decoupling carbon with protons, but not with fluorine. Fluorine is still present, fluorine coupling. So, look at the carbon which is attached to proton, this one. This has a large coupling, nearly 185 Hertz is seen here. And this carbon can also have a long range couple to this carbon, CO carbon. See, long range fluorine carbon coupling of 20 Hertz is there. Whereas this CH3, 1, 2, 3, 4 bonds away, 3 bonds away, this coupling is very weak, is not seen. We are seeing only as a double singlet because this carbon is coupled to only to proton that is removed because of decoupling. So this CH3 is only a singlet, and this directly attached carbon to fluorine is a doublet, and this one is a second bond, 2 bond couple, 2 bonds away, it is a doublet. So we can keep on, and I'll analyze one simple carbon-13 spectrum with proton decoupling. Let us look at this molecule. Proton decoupled carbon-13 spectrum of trifluoroacetic acid. We have to assign each and every peak here. First, of course, reference is TMS. No need to worry about it. What is this 3 peaks of nearly equal intensity? This is this solvent peak. Carbon-13 is coupled to deuterium spin 1, 3 lines of equal intensity. That is also well known. Now the question is why this quartet and why this quartet? Remember, this is CF3 carbon. Okay, this 1 bond CF3 carbon is very large, and that is why this carbon is split into a triplet. Triplet split into a quartet because of this 3 fluorine. So it is a quartet, 1 3 3 1 intensity. CF3 carbon is a quartet, and you are going to see this quartet. What about this carbon? This carbon is having a long range coupling with three equivalent fluorines. Long range coupling with this. As a consequence, this carbon is split into a quartet because of these 3 fluorines. Please understand now what is happening. Many interesting information you can get here. Directly attached carbon to 3 equivalent fluorines gave a quartet. This is 2 bond coupling. This carbon coupled to this 3 fluorine is going to be again a quartet. Is a long range 2 bond coupling, which is 44 Hertz. This is about 284 Hertz. Did you observe another interesting thing? If it was a CH3, we expect around 20 or 30 ppm. Whereas CF3, look at it, it is coming around close to 115 ppm. Why? Because it is attached to electronegative fluorine. As a consequence, there is enormous deshielding. As a consequence, the CF3 is coming to the downfield. So this is how you can interpret carbon-13 spectrum. But you may ask me the question, what was the need for decoupling here? None of them are coupled to proton. But there is a COOH proton. It may have a long range coupling with this or this. Of course, to ensure that it is broadband decoupled. So as a consequence, there is no proton coupling here. Okay. So there is a lot more we can talk about it. So today I will stop for the day. We have discussed a lot more about carbon-13 NMR, which is one of the most extensively used nuclei for all of you. We'll come back tomorrow and continue a little bit about carbon-13 NMR. How do you assign the different carbons attached to different protons, etc. by using certain technique called depth, inept, APT, etc. More discussion about that I will do later. And then I'll stop.